that total. This is a good chance for us to remind you about verification futures. We had a very successful verification futures last year in Reading, where we had over 300 people. There's actually 200 people on site in Reading, so it was quite a good networking event. Involved over 100 organisations in 21 different countries, 100 people remotely. And we're expanding that this week, calling it European Verification Week. And it's going to be in Windsor, France and Germany. And Harry Foster is going to be the keynote again. Harry Foster for Mentor is going to be our keynote. And he's just released his abstract. So if you go to our website, you'll see it on there.
But Mike Bartley, thank you very much for organizing this DV Club event. Thank you for inviting Breker. And Stefan, thank you for your interesting talk. I think it is quite fascinating how, in many ways, we are similar in how we have approached the use of graphs for verification. And I think it's equally fascinating how very dissimilar Breker's approach has been to graphs as far as Mentor is concerned. So I hope this audience has an interesting time comparing and contrasting what Breker styles itself as the SoC verification company. And we have taken this notion of graph-based constraint solving and focused very much on applying this to system-on-chip functional verification. In my presentation, I will talk to you a little bit about some of the challenges and myths around SoC verification. I will talk to you a little bit about the challenges that are faced and the problems that must be solved. I'll talk to you about our product, Trek SoC, whose main job in life is to generate embedded self-verifying C-tests that run on SoCs. I will further talk to you about how we support vertical reuse between the full chip subsystems and individual IPs, and how we have been working with UVM very much along the same concepts that Stefan talked about in terms of taking over the sequence drivers and UVM agents. Now I'll talk to you about a little bit about the visualization and capabilities of the tool itself. Okay, what's up? Okay. So when we talk system on chip, we are discussing, at Breker, we're discussing chips that have embedded CPUs in them. So the big mobile chips. Today they are, in fact, systems of systems, typically a dozen CPUs and some 300 IPs. Big scary things that frankly should never work, but somehow we make them work anyways. There are a number of myths that surround the idea of SoC verification. Those of us who've been in verification for a long time perhaps don't see these, and then yet again, sometimes we see these myths as things we hear from a man. One myth is, hey, if we know that we've completely verified all of the IPs in the system, surely when we stitch the whole system together, we know it's going to work. Stitch and ship should work. There should be no problems. Surely, since I know that each of my IPs work perfectly, all my fabrics work perfectly, my memory subsystem has been beaten to death, by induction, by pure logic, we know if we put this thing together, there can be no bugs in it. We know that if all the acceleration engines, if my camera and my image processor and my SD card controller, each unit has been shown to work correctly, surely when software hooks them all up into produce consumer scenarios, everything's going to work. We don't need to test that, right? And my favorites, power and clock management. All our chips have system management units these days. Yeah, we can test that as a unit bench, as an IP. Never mind the fact that it touches every single piece of my entire SoC. All of you on this call who've been doing verification for a while don't really believe this, but these are stories that come up, right? We're very hopeful that if we can, since we know how to do IP verification and possibly don't have such good solutions at SoC verification, we're hopeful that this will hold together. In fact, unfortunately, this is not holding true, right? Many bugs are being found in big SoC chips after tapeout. Here's a list of some issues that we've seen at various customers over the years. Right? Buses are working fine when you do single IPs at a time. When you start saturating the bus, things start to hang and you've got to introduce wait states just to keep things working. Or, hey, chip works. Each IP got the bandwidth it was looking for, but we started doing things in parallel. We saw that we can't push anything close to the bandwidth we designed for. We didn't do our performance tests. We realized we had problems. The bridge functionally looked fine when we were doing individual IPs. Do things concurrently and it just hangs. Addressing. We can't get addressing wrong these days anymore, can we? That's such a simple thing. We tested integration for every single IP. Everything worked. It turns out when you're doing interleaved accesses to two sibling IPs, there's some kind of a decode bug, and one IP grabs a read for another guy. Memory's been tested very well with loss randomization, but we made some bad assumption in the unit bench, and multiple access to the same bank break. One of my favorites. Hey, we plugged together two IPs, each of them worked fine. When we tried to put them in a producer-consumer scenario in software, only then did we realize, oh, wait a minute, one's talking big endian, one's talking little endian. Big problem. We've tested the clocking subsystem to death. It all works. Unfortunately, if you update the clocking system while the IP is executing, the system hangs. All examples of real bugs, right? All difficult things to test. All things that are difficult to generate SoC level tests for. Today for system-on-chip verification, we're generally seeing that work is done mostly by handwritten directed tests, typically written in C, that are compiled and run on the CPU. I don't know why, but every SoC integration team seems to have exactly 2,000 C test cases. It's never 2,500. It's never 1,500. And the combined suite of test cases typically focuses entirely on the basic IP integration testing, the so-called tip of the iceberg. We know as verification engineers that we've got to do much more than that. We've got to focus on multi-master concurrency, get all those IPs running at the same time, get multiple CPUs interacting with each other, sharing memory, making sure they're coherent. We've got to worry about data ordering across the network on chips. We've got to worry about cache coherency, power management, asynchronous inputs, lots of stuff. Okay, do I pay attention to anything coming in from? Maybe not. Okay, I'm sorry, the Citrix thing was saying something to me. Okay, and that's just getting multiple IPs running concurrently. What about interactions between those IPs? Typically, these IPs are designed to play in producer-consumer scenarios. Those are hard to write by hand. And then on top of that, we want to create a performance analysis cases to make sure that a system can actually handle the load they're supposed to in real life. We want to ask the question, hey, if I'm watching 1080p video on my cell phone, when a call comes in and I answer the phone, can I prove that the screen will not tear? These are the questions that Breker has set out to answer. So why is this such a problem? Well, we have solutions, don't we? Why can't we just use UVM at the SoC level? Well, this notion of having sequencers on buses, on interface agents, fine. Now we need virtual sequencers to coordinate those sequencers and those lower-level sequencers. It starts to get pretty complicated. And once you're starting to get a CPU in the system, we don't really have a way to get from the UVM flow to a C program that will run on the embedded SoC. Why not just write a test by hand? Well, frankly, we simply don't have enough time to write a number of tests that we need. And it is almost impossible to emulate multi-threaded operations in a test case by hand. Nothing's impossible. Enough time, enough people, you can do anything. But for a human being to sit down and write a multi-threaded test case that runs on bare metal without an OS and correctly interacts with I/O is very, very hard. Yeah, another question. Why not just run the production code? Let's just boot Linux, boot Android, and run all applications. In simulation, pretty hard. Way too slowly. But there's a much bigger problem. When you're running real application code with real OSs, that software is typically well behaved and keeps your design in the well-behaved area of operation. And it's very difficult to get the OS and the applications out into the corner cases that really stress your design. Yet it's not impossible. So you know it can happen, but it's very hard to test for it with the software stack on there. We need some way to create synthetic directed C tests that will go stress our hardware before we go put our software on. And possibly I don't need to tell this group that bug escapes from the DBT in a big SoC is incredibly expensive to the project. Things that are found by the software team, things that are found by your customers, they take weeks and weeks to debug, weeks and weeks to resolve what's happening. When the software guy finds a bug, he doesn't speak the same language as the hardware guy. Very difficult to communicate what's going on back to the chip fellows. So what can we do to help them? At Breker, we came up with this product called Trek SoC. What Trek SoC is fundamentally a scheduler designed to test and designed to create stress tests for SoC designs. So it manages multi-threaded test cases for multiple concurrent IPs doing producer-consumer scenarios, and as well as scheduling memory, scheduling I/O, scheduling the various system resources that are available, including power management. As input, this takes a graph-based model that we call a scenario model. So you see, graphs do eventually play into the story, and I'll get to that soon. The way the tool works is it generates a self-verifying C-test. In fact, a set of C-tests, one for each CPU. And it also generates this so-called events.rc file that is events that must take place on the test bench side while the C-test is running. And there's an automated mechanism for mailboxing event IDs across during runtime so that we know when to do various operations on the IOs while the test is running. So the big question becomes, how do we use these graph-based scenario models to drive the scheduler, which in turn generates all these test cases? So at Breker, when we started out, with the underlying technology that is a graph-based constraint solver. We looked at verification as the world exists today, and we said, okay, for some 20 years now, starting with Veracity and now in System Verilog and other tools, we have been using so-called SAT-based constraint solver, or a CSP constraint solver. This is where we have a set of numbers with some rules on those numbers. We say, okay, A must be less than B and C must be greater than the sum of A plus B. This was great for randomizing individual transactions, but it's clear that this has not been sufficient for creating entire scenarios because we were forced to introduce this idea of sequences. At Breker, we said, we're still going to do constrained random verification, but maybe you can introduce a more powerful constraint solver, and we proposed that we're going to introduce a graph-based constraint solver. The idea behind a graph-based constraint solver is we'll have a graph with various decision points, not so different than what Stefan just talked about. Yet we'll be able to put rules on the paths that may be traversed on that graph. If you visit node A, you must visit node B, or if you visit node C, you may not visit node D, and so on. So I want to talk a little bit about how we're going to apply those graphs, apply such graphs to verify SoCs. So finishing my slide over here, I guess, the big point over here is to generate heavy concurrent producer-consumer tests with multi-master concurrency. And we're quite proud of the quality of the C-tests that we generate. They are quite well commented, quite human readable, and my favorite quip when demonstrating this tool is to say, okay, here's a test that's generated by my tool, and the only evidence you have that it was generated by a tool and not a human being is no human being would comment your test as well as my tool did. So now, not only are we able to generate tests for an SoC with this C-test flow that I'm showing you over here on the left, from the same models, we can also drive transactional tests for, say, a UVM environment or an OVM environment or anything else that's transactional. We can further peel off single models for individual IPs and apply them to unit benches for the IPs themselves. And this has proven to be very powerful. For some of the customers, we're seeing the graph-based model used first at the IP level and then combined with other IP models to go up to the system level. In other cases, we're seeing uptake of the tool first at the system level using so-called sparse graphs, where at the system level we are not so worried anymore about trying to verify the corner cases of the IP, and we're much more interested in seeing whether the IPs play well together. And we start with those sparse graphs. As they start to become more valuable, they get demoted down to the subsystem and IP levels, and we've seen proliferation in both directions. So let's get on to the actual application of graph-based models to an SoC. So let's talk about a classic SoC, and where perhaps I have a camera, I have an image processor, and I have some kind of SD card controller. A typical producer-consumer scenario in such a chip might be that the camera produces some data from the CCD and puts it in a buffer. That data is then consumed by an image processor to perhaps produce a JPEG image, and then the resulting second buffer of data is consumed by an SD card controller and written out to the SD card. So SoCs are all about verifying data flows through the chip. How can we model those data flows in a graph? So here's a picture of a graph. The important piece is to know that the purple diamonds are decision points in the graph. And for individual driver scenarios, models for each IP, the top-level structure of a scenario model is always pretty static. You will typically start by configuring the IP. You might make some decisions about how big a transfer you want to do. You might have to go allocate your source and destination data, memory buffers, make some mode decisions, and so on. You will enable the IP. Then you will wait for a completion, either an interrupt or a pull, depending on which mode you want to run in. When you get that completion, you are now prepared to either check or use the outputs, which might be in memory registers or some I/O output. So this is the typical view we see of individual IPs. And we have come up with a flow where the IP model only knows information about the IP and nothing about the system. The point being that we're then able to stitch this together and graph-based scenario models for each of the IPs at the system level to go to the entire system. Data from SDIO card, we might start by saying, okay, I want the image processor to maybe process some data, and maybe he's getting that data from the SDIO block. And we just chain these graphs together. One detail that must be handled over here for it to work is the image processor and the SDIO card must be working in some coherent scenario. You can't have the image processor working perhaps in low-res mode while the SDIO card is trying to provide us with a high-res image. And that's one example of where the graph-based constraint solver comes in. We can make some decision on what path we work with the image processor, and that can be used to constrain what paths in the SDIO model we might use to provide data to that image processor. This approach has turned out to work quite well at a large number of companies who are all doing the big embedded SoCs, mostly going into cell phones and tablets, and in some cases going into large high-end server machines. The graph-based constraint solver has worked real well for us. It allows very large search spaces to be represented with fairly small graphs. And I think more than anything else, it's worked out very well because this approach of thinking about what behaviors we want to see and how to map them onto the inputs we need and relating these with graphs has turned out to be very natural for humans. They are typically handled in UVM agents, and we're not so worried about trying to cover the protocol level randomization. What we are focused is in the system level self-verifying C-test cases. Once you have those, you can scale them across any environment that can run a C-test. And of course, the big advantage has been able to do the clean, seamless rules from IP to SoC, where we, from the same model, we're able to generate transactional tests at the IP/UVM level, and just push a button and generating those transactional tests restart is supported for the tool itself. So here we start to see some commonalities and some differences on what has already been discussed. In our user interface, we always keep a tally of how many possible paths there are under any node in the graph that you've clicked. Of course, you can visualize the graphs. There's been a long time joke running between me and my friends at InFact as to why Breker decided to draw the graphs left to right and why this were top to down. I don't know. On our graphs, we overlay the constraints that have been applied on the graph, and here you can see the various colored lines showing you that if you visit certain nodes, you must visit other nodes and so on. We're finding the visualization of scenario models to be a big benefit. We're seeing for the first time that DV engineers can really express to their managers, look, here's what I'm testing. And DV managers for the first time can really understand what DV engineers are doing and going, okay, yeah, you've tested most of the cases, but you forgot that you didn't cross this feature with this other feature. We came up with this idea of a pre-simulation reachability analysis capability, which is basically trying to ask the question, given all the constraints in the system, what paths in the graph are still reachable? This is answering an age-old question in constrained random verification, where if you over-constrain the system, you can accidentally get interactions and kill half your search space without meaning to, and you might not figure this out till very late. With reachability analysis, you can apply constraints and get immediate visual feedback on which paths are reachable to make sure this is what you meant. Right? Even as an experienced user, I'll sometimes be putting in what I think is a small constraint to perhaps work around some bug that we're waiting for a fix on, and it interacts with some other constraints and half the graph goes red, and you go, oh, okay, no, that's not what we're meant to do. We must. And some interesting conversations went down on what is the best way to achieve coverage. So as we're generating test cases, we keep track of what paths through the model have been exercised. We give you back roll-up information is like this hotspot graph of what's been, what nodes have been visited and how often they've been visited. We also have facilities for doing cross-coverage analysis of have I crossed all possibilities for decision A with all possibilities for decision B. And we also have a notion of coverage by construction, where you say, okay, I'm interested in hitting all of these cross coverages plus all of these nodes, and the tool tries to go find the minimal traversals needed to go hit those coverage points. Now, typically, these graph-based models that we see search spaces of the order of 10 to the 300 for even just a few IPs involved in SoC. It's very easy to describe very large spaces with a graph, which is good. And the fact is, as DV engineers, we face every day problems where we have a search space of 10 to the 300, yet in the lifetime of a project, we'll do how many test cases? 10 to the 7, 10 to the 8. If we get to run 10 to the 9 test cases, that's 1 billion test cases. 10 to the 9 samples out of a space of 10 to the 300 is about 0% coverage. Yet we must prove with that 0% coverage that we have no bugs. So the game is all about finding the right points to go test. We think the way we have introduced this, these graph-based models where we begin with the end in mind. We say, think about what outcomes you're looking to cover and then solve for what inputs you need to achieve that coverage, has achieved 2 important goals. First, it has worked very well for human beings. We do well at thinking about our outcome spaces, our input spaces, and then relate them using graph-based constraints. We find them intuitive. And second, it allows us to make the best possible use of the few simulation cycles that we have in the lifetime of the project. So in our worldview, we use this coverage by construction pretty much to do a smoke test to go make sure everything's been touched once. But then we really do rely on constrained random verification, just like we've been doing for 20 years, just with a different kind of engine to go after the hardcore verification.
Hello, Adnan.
In summary, I'm on my summary now. Okay. So in summary, SoC verification, stitch and ship does not work. Verifying individual IPs does not mean that your entire system works. there are many points of convergence across IPs, on the buses, on the memories, on interrupts, on sideband signals between the IPs, on IOs, on power management. These all have to be tested at the system level. Trek SoC was designed specifically to go after this test case. It uses these graph-based models as inputs, and that input drives a scheduler that knows 80% of what there is to know about verifying the system in general. You can generalize the problem of SoC verification if you say SoC verification is about moving data, and we can build a tool that automates concurrent producer-consumer data chains through a system. Now all we need is to know what are the rational data flows through a system, and what are the steps we need to do for each IP to get them to move the data. And I've shown you how we do the IP level driver models and how we do scenario use cases by chaining those IP models together. This is proven to be quite powerful in generating deep state test cases in big SoCs. And finally, we see that this graph-based approach that we talk about begin with the end in mind. We ask our users to think about what are the behaviors they want to observe, and then how to create these behaviors. This has proved to be quite easy and natural to learn. The graph-based approach has given us a mechanism that allows for incremental rollout of models. So we can start with a very sparse graph that has only some randomization initially, and that is already useful, short time to first bug. And then as you add information to the graph, you multiply its search space. So very quickly you get to start searching very, very large search spaces. And finally, and perhaps most importantly, these graph-based models have really helped communication within teams and within all the stakeholders involved in the verification problem. So thank you very much for your attention. I'm open to any questions that we have time for.
Hi, Adnan. Yeah, thank you for that. We just have one question in Bristol from Jeff Barrett of Broadcom.
Yeah, thanks, Adnan. Okay. Yeah, one thing that's burnt me with these things in the past is proprietary languages from a small company. If the company crashes and burns, then you end up with a load of verification IP that's in a no longer supported format. So we've heard from two different companies, and I suspect you've both got somewhat different input languages for what must be more or less the same concepts. So are there any commonalities between what you and Infact are doing, and are you putting any effort into standardizing your languages?
Great question, Jeff, and thank you. At this point, no, neither of us have gone down a path of trying to make this a common language. I do think that we have approached the problem in rather different ways, and the world will evolve, and we will see what goes on. But I think the important question is, yeah, you've got to worry about betting on small companies, but maybe we will see soon that Breker is not such a small company. We've had quite a lot of success over the last few years with some 45x growth in the last 3 years. You will, in about a week or two, see a press release go out that we just closed $5 million in VC funding. We are seeing quite good uptake on our SoC verification solution, so I think you'll see us around for a long time to come.
I think we're going to go to Cambridge now for questions from Cambridge. Do you have any questions, Brian?
Any questions from the room?
Right. Because the constraint solving is offline, how does it interact with the deep state?
So the question was from Sean. So because the constraint solving, sorry, because say it again. Because
constraint solving is offline,
yeah.
So you're generating C test.
Yeah.
So there's no interaction with the design of the test during the solving of constraints. So how are you pushing the corner case scenarios in a way that...
So because the constraint solving is offline, how are we pushing the corner case scenarios?
Excellent question. Very good. So in the time I had available, I did not have time to walk through how it is that we actually use the graph-based constraint solver to capture the verification space, but I'll try to explain it in a few words, and then maybe we can get some intuition for why we're able to do these deep state operations. So let's consider that we want to think about an. I'm getting quite a lot of background noise. Okay, and so we think about SoC verification in terms of the data flow through the design. So these are the use cases, right? The data going from the camera to the image processor, out to the SDIO card controller, and so on. So we are possibly, actually, let me use a different example. An IP might have, say, SoC might have a display unit, right? You've got to see something on the screen. That display unit might be displaying information from the output of the image processor if you're looking at a photo. Or it might be using data from the output of a video decoder if you are watching a movie. Great. The image processor might get data from maybe a USB dongle or maybe from an SDIO card, right, to static storage locations. Oh yeah, wait a minute, the video decoder could also be getting data from either of those locations. And what we have here is a graph of possible data flows through the system. Okay. So we're able to directly map that graph of data flow through the system. Okay. Each node in that graph in itself, you can push down into it, and now that's a graph of how we can manipulate the IP to affect that node of the data flow. And those are giving you the possible paths for individual scenario. So I think with this, you can go after quite deep state in just how the IPs can interact. But the real deep state is coming not from the individual iterations to the graph, but the fact that we're able to schedule that work concurrently across multiple CPUs and create a lot of traffic on the fabrics and on the memories. And just by hammering the chip hard, we find ourselves in the deep state cases, right? I mean, it's sort of a difficult question to answer explicitly. You're right, we are not probing into the design to say, hey, we're watching this particular bit and this bit tells us to go do something. Typically in producer-consumer use cases at the SoC level, we as human beings don't have good things to look at to go after that. And what we're much more interested in is the relative scheduling, the relative concurrent scheduling of different events that will hit the same interaction points. And that's in fact what the scheduler is specialized to do. So maybe it's a combination of those two things. But what I can tell you is that we are seeing the deep state bugs, and sometimes it's quite interesting, the bugs that we'll find.
Did I answer your question, Sean?
Yeah, I think what you're trying to explain is that you can find corner case, or you can define corner case scenarios. I think, Adnan, what you're trying to say is you can find corner case scenarios that you know about, but what about the ones the developer hasn't thought of? How are you going to find those?
Oh, good grief. If we say we're just looking for corner cases that we know about, then we're shot, right? I certainly don't believe that that's what we're doing. We think we're very much following the footsteps of constrained random verification as it has stood for a very long time. And all we're doing is replacing the notion of a CSP constraint solver that's based on rules and numbers with a graph-based constraint solver that's rules on how you traverse a graph. But I still think you're just defining entire input spaces, all possible outcome spaces, and trying to reach them randomly, hitting them randomly. See, in an SoC, and the problem starts to get more complicated, right? Because you're trying to generate these embedded C programs that are trying to get all these IPs to go concurrently with the right randomly selected timing edges to go after corner cases in the system. And I think this is pretty hard to hit with the technologies we have right now. But philosophically we're still doing constrained random verification.
Okay, I'm conscious we're probably running out of time here, Mike.
Okay. Okay.
Have we got time? Sorry, have we got any more questions from Cambridge? We've got time for one more.
Yeah. Okay. Just quickly.
So, how do you describe parallel paths in the graph-based tree?
In fact, we don't even make you do that. You described the scenario model in terms of possible data flows through the chip, and those paths are fed to a scheduler. You have the possibility of constraining the scheduler to say, okay, I want these things to run on these CPUs or on these threads or so long after the previous step in the operation, but that is very much automated.
Okay, thanks, Brian. Just one very quick question, Adnan. Is this integrated to UCIS or not? It's a question from Bristol.
Yes. Instead of trying to figure out UCIS and trying to you're talking about the coverage database, right? UCIS. I'm answering. Is that correct? Mike, help me out. UCIS, the coverage data, the coverage API.
Yeah, the unified coverage database.
Yeah, yes. So instead of trying to chase that down, what we did really was come up with a way to export what we called stub coverage files for system Verilog. In these files, we define the cover points and trigger them the right amount of time.
You're breaking up there, Adnan. I think your microphone drifted out. Just a quick answer. Is it a yes or no?
We did not go after the UCIS API. Instead, we went down a path of exporting stub system Verilog files that define the cover points and trigger them the right number of times. This allows you to run that system Verilog once and pick up all the coverage from the tool in your existing environment without needing integration from it. In fact, we did this on Cadence's recommendation.
Okay. It's interesting. Okay, thanks, Adnan. Thank you very much for an interesting talk, and also thank you for the pizza in Bristol. We're switching across to. We're going to switch across to Levy. We're going to switch across to Levy.
Clap for the pizza. I demand the clap for the pizza. There. Okay. Thank you.